morning Year 8 and welcome to the third and final part of your limestone practical. By now you should have planned your method and been given the opportunity to adapt and improve your method so you can say how you would have carried out this practical, investigating the amount of limestone in different samples of rock. There were some very good methods, there were some that may have worked given a few more details, and there are some that I don't think would have worked. Nevertheless, I remind you the whole point of this was that you got the chance to plan your own experiment. Now in a normal year you would have been given the chance to carry out your experiment to see how well it worked. And we over the last few years have had a variety of weird and wonderful ways to try and do this, from balloons to year 13 back titrations to the sorts of methods that you're going to see today. But unfortunately, due to lockdown, we can't let you loose in the lab, so we have done the experiment for you and you are going to write up based on that. So watch the video, take notes if you need to, and then be prepared to write up this experiment as done by Mr. Reeves and Miss Richardson. Okay, so Year 8, welcome to this second part of your limestone practical. Now, however you decided you were going to investigate the calcium carbonate content of the different rocks, this is a method that we're going to teach you. It produces good results, it uses easily available equipment, and it's easy to understand what's going on. So we've got our three varieties of limestone. We've got Dover limestone from Kent, we've got Malham from Yorkshire, and we've got Castleton from Derbyshire. And we need to investigate how much calcium carbonate is contained in each of those. So as we suggested, we're going to react those with acid, and we're going to see how much carbon dioxide is produced. And in order to do that, we're going to use a method which is called collection over water. So in each of the ice cream tubs, they're just full of water, and we are going to first of all invert a measuring cylinder which we're going to use to collect the gas. We're going to fill that measuring cylinder absolutely full of water, and then we are going to carefully but quickly turn it upside down into the trough of water so that it remains full of water. And look at how both Mr. Reeves and Miss Richardson did that. They put their hand over the end, they used a bung to help them, and that measuring cylinder that Miss Richardson has just inverted and the measuring cylinder that Mr. Reeves has inverted are both absolutely full of water. So we'll show you a diagram of how this is set up, but those measuring cylinders are full of water. The key thing here is there's no air in those measuring cylinders. So we know if we measure 10 millilitres of gas, then that will go down to the 10 line on the measuring cylinder. The next thing we have to do is we've got a conical flask and a delivery tube being modelled there by Mr. Reeves, and we need to get the bottom of that delivery tube into the measuring cylinder so that any gas that goes down that delivery tube is collected in the measuring tube. And we just need to make sure that that can reach our conical flask. Now I want you to think, what is one of the most important control variables? What do we need to ensure that we keep the same every time we do this experiment? And hopefully you are screaming at the screen that we need to use exactly the same mass of rock each time. And we have selected an appropriate mount. So Mr. Reeves is going to measure out 0.4 grams of Dover stone. Dover limestone, and Miss Richardson is going to measure out 0.4 grams of Castleton limestone. So being as accurate as possible, we're going to measure out 0.4 grams of limestone. Okay, so now that we've set up our measuring cylinders and our delivery tubes, and Mr. Reeves and Miss Richardson have weighed out 0.4 grams of their limestone, we need to work out a way that we can quickly mix our acid and our limestone in the conical flask. Because what we need to make sure is that no carbon dioxide gas can escape from the conical flask before we get the bung on. We need every single milliliter of gas to go into the measuring cylinder so we can be accurate. So Mr. Reeves has got specially small weigh boats that will fit down the neck of the conical flask. So first we're going to measure out our hydrochloric acid. We've done the calculations, and 50 millilitres of acid should be more than enough to react with all limestone. Actually, we worked out about 10 millilitres is enough to react, even if the limestone is 100% calcium carbonate, so there should be no problem with the acid running out. Now, when Mr. Reeves and Miss Richardson are ready, they're just going to quickly drop the weigh boat and the acid down the neck of the conical flask and quickly put the bung on. There we go. And we can see instantly both of these reactions working well. Mr. Reeves, his reaction is definitely generating more gas than Miss Richardson's reaction, and we need to keep these things moving so that the reaction proceeds. Now remember, we're not timing how fast the gas is produced, we just need to work out what is the total volume of gas that's being produced in these reactions. So every few seconds they're going to shake the flask to encourage the reaction along. So we can see now that Mr. Reeves' sample, which I believe was the Dover from Kent, has produced quite a lot of gas. Reading the measuring cylinder, sir, how much gas is that so far?
You're looking at around 65 centimetres cubed.
65 centimetres cubed. Miss Richardson, who had the Castleton from Derbyshire, what's your reading at the moment?
13 centimetres.
13 centimetres cubed. So at the moment you might be saying, oh well, the Dover clearly has more, but remember, we're not interested in how fast the gas is being produced, we just need to measure the final volume of gas that is released from the reaction. So we're going to keep going, we're going to keep swirling until no more gas is produced in this reaction. You might be worrying about the weigh boats, but the weigh boats are inert. They're not going to react with the acid. They're not going to stop or hinder the reaction. They're not going to cause any error in our measurements. And do we think that's pretty much over, both of you? Not going to give any more?
No.
Okay, so Miss Richardson, what is your final reading?
My final reading is exactly 15 centimetres cubed.
15 centimetres cubed. And Mr. Reeves, what is your final reading?
76 centimetres.
76 centimetres cubed. Now,
I'm going to adjust that because I just got an extra bubble.
Oh, an extra
16
16 centimetres cubed. Now, Mr. Reeves and Miss Richardson are excellent chemists. So what are they going to do now? Yes, you're right. They're going to repeat the experiment 2 more times to check that they get results that agree. So, Tweedledum and Tweedledee have repeated their experiments. I actually made them do each other's experiments just to check that they weren't cheating. And how many millilitres did you get this time, Mr. Reeves?
I got 13.
13 millilitres, which isn't bad, given that Miss Richardson got
60.
16 millilitres. So actually, quite a reproducible experiment there. Miss Richardson, how many millilitres did you get?
I got 89.
And just to show you what this looks like, you can see there 89, actually about 90 by now, millilitres of gas on that tube, compared to how many the first time around, Mr. Reeves?
78.
78. So that gives you some idea of how reproducible this experiment is. So we will record these results on a table for you on the next slide. But there you go. This is how we collect gas over water and how we can work out which of our rock samples has the most carbonate in it. Thank you very much, Ms. Richardson.
My pleasure.
Thank you very much, Mr. Reeves.
No problem at all.
Okay, well, for many of you, I expect that experiment is quite close to what you had envisaged. So this is the scientific diagram. Notice that the diagram is completely two-dimensional. It is drawn using straight lines. And it is fully labelled. A few extra things to notice. Notice that the water is flat, so liquid levels are always flat. Not wavy. If you look at a glass of water, the glass doesn't have wavy water, it's a flat line. Notice that the delivery tube down here is under the measuring cylinder. And that is of course important, because if it's not under the measuring cylinder, it's not going to collect the gas. Notice that the bottom of the measuring cylinder is under the level of the water. So this has to be true or the water will escape. So measuring cylinder is submerged. Submerged in water. Okay, these are not labels you need to add, but they're things you need to pay attention to when drawing the diagram. Notice that the delivery tube goes through the bung. Loads of you had a solid bung, which of course wouldn't let any gas out. You need to make sure that the delivery tube goes through the bung. And finally, look at how the clamp is drawn. It's nice and neat, out of the way, but it brings across the idea that you need to clamp that flask. Also, we don't need to heat this experiment. Loads of you were under the impression that we needed to heat it to make this reaction go, and that is true, it would make it go faster, but we don't need to heat this conical flask. So when you draw this diagram, just pay attention to all of these things. Here's the results table. We've got what are called the header cells at the top. And they tell you what's in the various columns of the table. And look, volume of carbon dioxide collected in mil. This is where we put the units. We put the units at the top of the table. We've got test 1, test 2, test 3, and then we've got the average on the right hand side. So these are the ones you saw in the video, 78 millilitres, 89 millilitres. The third run was 85 millilitres, and that averages quite nicely to 84. Here, 13 plus 16 plus 15, again you saw these two, 13 and 16. Well, if you add up all of those numbers, you end up with 44. 44 divided by 3 is 14.666, so on. 14.6 recurring. Now we don't write that in the table. We don't write an average that is more precise than the data we collected. So we use the same number of figures as the data we collected. So hence we write 15 as the average, not 14.66666. Down here, 52, 48 and 45. You didn't see these, but these were experiments that were carried out by Miss Richardson and Mr. Reeves off camera. And again, they average to 48.333. So adding these up, 145 divided by 3 gives you 48.3 recurring. Well, again, we don't write that. We give the nearest integer because these have been recorded. Okay, so we give the same number of figures in our average table. And this is true whether you're doing chemistry, biology or physics. You should never give an average that is more precise than the data you collected. And you're going to need to copy down this results table as well. Having written down the diagram and the results table, you need to write a conclusion that is quantitative. Remember, what you are trying to work out is which sample of rock contains the most limestone. Okay, and you need to answer that question. And by quantitative, I mean you need to put numbers on it. So not just one has more than the other, but how much more. So put numbers on it. As in, Dover rock has 4 times as much carbonate as Malham rock and about twice as much as Castleton. That's not true, okay? But that is an example of the sort of thing you might write. And justify your conclusion with data from the table. So having written your conclusion, say, well, I know this because Dover rock produced an average of 84 mil of gas, which is 10 times as much as the Malham rock, which produced 9 mil of gas. Again, this is not true, but it's showing you the sort of thing that you've got to write. So using the data in your table, write yourself a quantitative conclusion, support it with data from the table. Finally, now this is hard. This is something that Year 8s really struggle with because you've only ever been told to do something, and actually I know what you guys are like. You never think about the method or the experiment. If you are given a practical to do, you just do the practical. You're what's called minds off. And what we're trying to teach you to do is we're trying to teach you to be minds on when doing a practical. You should be thinking about the practical and whether it's a good practical and any problems with the practicals. So you need to say, was this a good experiment? Do you believe the results? And why? Okay, so don't just say, yeah, it was good. You've got to say why you think it was a good experiment. Not were Mr. Reeves and Miss Richardson good at doing it, but was the experiment itself good? Can you think of 3 sources of error? These aren't mistakes, not mistakes, so it's nothing that Mr. Reeves and Miss Richardson did that was wrong, but anything that, you know, problems with the chemicals, problems with the method, problems with the equipment, things that they couldn't help. reasons why the results might not be perfect, and at least one of those was mentioned in the practical video. A reason why the volume of gas you collect isn't going to be 100% accurate. But can you think of 3 reasons that this wasn't a perfect experiment, even if Mr. Reeves and Miss Richardson had been perfect at doing it? And based on that, can you think of one way to improve the experiment to get more reliable results? So here's the experiment. How would you have made it slightly better? Not what would you have done that Mr. Reeves and Miss Richardson did wrong, but how could you make the experiment itself better? And this is hard because actually it takes training for you guys to stop just doing what you're told and start thinking about why that might not be the best answer. But see if you can do it. See if you can come up with a way to improve the experiment. So to sum up what you need to do, in your exercise books, number 1, copy out the experimental diagram using a pencil and ruler to draw the equipment, being careful to label it and being careful of all the things I highlighted that are common mistakes students make when drawing that practical equipment. 2, copy the results table exactly as I drew it, with units in the header cells. Do not ever put units in the results cells. Even at GCSE students still do that. No. Write a conclusion for your experiment, full sentences, that is quantitative and supported by data. I think Malham had 4 times as much calcium carbonate as Kent, because it produced 4 times as much gas, 60 centimetres cubed compared to 15 centimetres cubed, or something like that. And finally, write an evaluation of the experiment. And I accept this is hard, but you do need to learn how to do it. Certainly by GCSE, so you may as well start practicing now. Do you believe the experiment, the reliability? What was it about the results, perhaps, that told you whether or not you should believe them? Can you give 3 sources of error, 3 reasons why this experiment wasn't perfect? And can you give 1 suggestion on how you would improve this experiment? And that is it. Once you've done those, that's the end of the Limestone practical, and we now just need to wrap up the project and the entire topic ready for your end of topic test. Goodbye.